Thank you, everybody. Thank you also for the terrific walk-up music. That was my kids were very excited the fact I was going to have my own walk-up music here. Great venue. Thank you to the Couchbase folks. I should tell you, full disclosure, I'm a Broncos fan. I grew up in Denver. My therapist says that it's actually very good for me to confront my fear of the 49ers by being this close. So if you see me twitch a little bit, if you see me 55-10, 55-10, 55-10, that's what's going on. So I just want you to, full disclosure again, I am medicated, it should be fine, but I just want you to be aware of that. So again, it's great to be here. And we're going to talk about running Couchbase and getting Couchbase performance and getting Couchbase elasticity in this new world. But before we go into the new world, as I want to do, let's go back to the old one. And full disclosure, I worked for Sun for 14 years. So this is a little bit like showing you a picture of my mother here with this. I don't know if people know what this machine is on the right. This is the E10K. And this is elastic infrastructure circa the dot-com boom, circa the last bubble. And back in the day, if we wanted to scale infrastructure, we just made it bigger. It was one machine, and we just got a bigger and bigger and bigger and bigger machine. And you had folks like eBay that started out on a little bitty machine, and they just made that one machine bigger and bigger and bigger until they were running on one of these things on the right. And then, of course, it crashed, and they were down for 22 hours, and it was on CNN, and blah, 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 blah. But this is the way we actually scaled infrastructure. And actually, I don't remember Boo.com. Boo.com was one of the early .com flameouts. Boo.com had one of these. They were starting off as a little startup, and they bought one of these things, which is the size of a 747 pallet, by the way. These are a big machine. They bought one of these and just put one CPU board in it. And then as they scaled, because they were going to conquer the world, of course, as they scaled, they were going to add more CPU boards. That is the way we scaled infrastructure in the dot-com boom. And it was a glorious thing from a vendor perspective. It was really not a glorious thing from a customer perspective because Boo.com spent more on Sun gear than they ever made. God bless them, really, but it doesn't actually work, right? It's not actually a viable business model. And when we hit the nuclear winter, of course, we know that there's another winter coming, but when we hit the last nuclear winter of the dot-com bust, this was no longer acceptable. And instead of having these giant machines, single machines that we would scale, we actually became very attracted to commodity hardware. And instead of one machine, we're going to scale out a bunch of machines. And we're going to rack and stack. And if you want to actually scale out your infrastructure, you're going to add more physical machines. And because this was so economically compelling, we actually changed our software architectures to actually accommodate this model. Because there are lots of advantages of having many, many, many smaller computers as opposed to one galactic computer. One is that, of course, you're more available, right? You're building a distributed system. It's more available, you can scale it, and so on. So there are a lot of economic advantages, but it required us to totally rethink the way we did our software. And that's what we did in the early 2000s. In the early 2000s, we basically rewrote everything. And we don't think of it this way, but that's actually what happened. And the genesis of Couchbase, you can actually see back there with Memcached. And Memcached, of course, scaling to many, many nodes. And if you wanted to make your Memcached faster, bigger, and so on, you just added new nodes. And then, of course, Couchbase came along, added persistence to that, and so on. So we started to build these infrastructure, these architectures that leverage this scale out, adding physical machines. And this was great. But this was so great that you begin to ask yourself, wait a minute, why am I actually adding a physical machine? Why do I have to take a physical server? Well, if these things are commodities, if I don't actually care about them, if I don't love them the way that I love an E10K, modulo eCache parity errors, if I don't love them the same way, maybe I don't care if I own it. Maybe I don't need to physically own it. I don't need a physical data center. Maybe I can go rent this from someone else, and I can actually just spin up my compute elsewhere. I can actually virtualize my compute. Now, from a computing provider's perspective, this sounds great. I want to provide you compute. I want to actually realize those economies of scale. But in order to be able to do that, I'm going to have to virtualize in the stack. Because in order for this to be economically viable, we need to have multiple tenants actually sharing the same physical infrastructure. So the question is, how do we do that? Where in the stack do we virtualize to allow multiple tenants to share the same physical hardware? And the first answer is also the oldest answer. Hardware-level virtualization. And hardware-level virtualization means I'm going to give you, as a tenant, your own virtual hardware. And you, on top of that hardware, you are going to place your own operating system, and then you'll run your application stack on top of that. And actually, the genesis of this is actually very interesting. The genesis of this, like so much in our industry, actually goes back to IBM in the 1960s. And IBM was developing what is really probably still the most important single computer of all time, the System 360, in the mid-60s. And the System 360, so named because 360 degrees, it was going to encompass all of computing. It was going to pull together all of these disparate computing lines, the 1401, the 1620, the 650, and so on. And they were going to pull it into one galactic machine, the best of all machines. But of course, it wasn't going to run all the old software. I mean, why bother running all that old dirty software? Software, you can rewrite your software for our glorious instruction set. But of course, people weren't so into that. And so they came out with the System 360, and people weren't really buying it because they had all their old 1401 infrastructure. And into this gap came Honeywell, a company that actually used to make something other than thermostats. And Honeywell actually made computers. And they had a computer called the H200. And the H200 was a computer that people weren't very interested in, but they said, what if we actually make this look like an IBM 1401? And so they actually developed hardware-level virtualization for the H200. And so you could take your 1401 software and run it right on the H200. And in classic mid-60s fashion, I love the name of this thing, it's the Liberator. I mean, don't you miss the Cold War? I feel like, I mean, for me, and I know I'm getting old because I actually feel, I think fondly of the Cold War, but it's like the Liberator. That's something we would call like an ICBM back in the day, you know? Anyway, so they had the Liberator, and the Liberator, now you can run your 1401 software on a much faster transistorized machine, and that machine takes off. IBM realizes, wow, this hardware-level virtualization is important. They add hardware-level virtualization to the System 360. And hardware-level virtualization is great at doing that. It's great at taking this legacy software, and you can just drop it right onto new hardware. It's terrific at that. But that's kind of where the advantages end. Because the problem with hardware-level virtualization is the abstraction is the actual hardware. You've got to have your own operating system that you place on top of it. And if having a second operating system, an operating system on top of virtual hardware, on top of another operating system on top of the actual hardware, if that sounds to you like that's not going to make anything faster, you're right. That, of course, makes things much, much slower. Because if you want to talk to the real world, you can't just talk to the real world via the operating system. You talk to the real world via your operating system, your second operating system, that then needs to trap into the hypervisor, that then needs to get out into the real world. I/O becomes this ridiculously convoluted path to actually do anything real. It induces latency. It also inhibits tenancy. Because when you give DRAM to a virtual piece of hardware, that DRAM is all gone. You don't have a way of leveraging that DRAM across multiple tenants. So this thing really, it's great for running 1401 software. And if you've got some 1401 software that you need to run, I strongly encourage you to use hardware-level virtualization. But beyond that, it really begins to count against you. And you're like, okay, I get it. Hardware-level virtualization, like no, I won't do that. But I mean, we wouldn't do that today. It's like, yeah, actually, funny story. You are doing that today. If you are spinning up anything in the cloud, you're actually spinning up virtual hardware. When you're running on Amazon EC2, that's virtual hardware that you're running your own operating system on. When you're running VMware, you're running virtual hardware. So again, great for certain things, and actually good for elasticity, but terrible for performance, terrible for tenancy. Okay, so that's hardware-level virtualization. Do we have any other choices? We can go platform-level virtualization. We can go all the way up the stack. That gets us into what I call the Google App Engine problem, where you develop something that's great for developers way up here, but you can't actually do anything real with it. When you actually try to go build something that's not a toy, I'm trying not to be pejorative here, but it's not working out. When you try to build something that is not a toy, you find that the abstractions become confining. And you certainly can't take like, oh, Google App Engine, I love that. I'm going to run my Couchbase on my Google App Engine. It's like, no. What? No. That doesn't even make sense, right? So no, this is at too high a level of abstraction. So if platform-level virtualization is too high and hardware-level virtualization is too low, of course, OS-level virtualization is just right. OS-level virtualization is where you've got a single operating system running on the hardware, and then for tenants, you give them a virtual operating system. You give them a virtual system call table. Looks, feels, smells like a machine, but it's not. You're sitting on one OS kernel that can actually see all applications. Your applications are running directly on the metal, but they are containerized from one another. They can't see one another. Tenants cannot see one another. And this can be made totally secure as hardware-level virtualization. This is a huge win, because now you've got something that boots like a bandit. You've got something that is actually, when you do I/O, it's just a single operating system you're talking to, and then out over the wire or out to the spindle. It's a galactic win across the board. And this is a model that was actually pioneered by FreeBSD with jails. Solaris picked this up, saw the success of the FreeBSD model, took that to the logical conclusion with zones, and then it was aped, very intentional verb, by Linux with containers. There actually are no Linux containers. There are namespaces and C groups. Linux has done kind of a poor imitation of containers, and without an eye on security and multi-tenancy, and that's going to become important in just a second. So in terms of OS-level virtualization at Joyent, OS-level virtualization is deep in the animal brain of Joyent. It is the organizing principle of Joyent. Joyent's been around since about 2006, even earlier, but we've been using OS-level virtualization in production for nearly a decade. Nobody has done more OS-level virtualization than we have. And actually, kind of perversely, we actually added hardware-level virtualization to the stack in 2011. So I and a couple other engineers went in and actually added hardware-level virtualization. We ported KVM to our operating system, Sporto, and when it was kind of like being a carnivore and going for a tour of the sausage factory and coming out a vegetarian. Because I've seen inside of the KVM sausage factory, and I've seen the number of squirrels that fall into your I/O, and they just ship it out anyway. So, I mean, enjoy the tang if that's what you like, but I'm telling you, there's a lot of vermin in your hardware-level virtualization. Horrifying, horrifying vermin. Not for me. Thank you very much. I'm going to stick with kale. Kale, of course, being OS-level virtualization. And so we know the strengths of this. We've seen the strengths of this, and we were steadfast believers in OS-level virtualization, and we were always emphasizing the operational characteristics, the performance, elasticity, and tenancy, and so on, but we were actually a lone voice. And we were a lone voice until a company that you haven't heard of, a company called .cloud, came along and saw they wanted to use containers as a substrate for their platform as a service. So they began to use containers for that, and people weren't very interested in their platform as a service, but they were very interested in the orchestration software that they developed around those containers. And the software that they had developed for that became very interesting to people, so the company promptly changed its name to Docker, which is the name of the software that they developed, and Docker was born. So this is in the middle of 2013. They open sourced Docker, and Docker is really interesting because Docker also believes in OS-level virtualization, but is coming at it from a different angle. Instead of coming at it from the operational characteristics, Docker is coming at it from the perspective of the developer experience and the ability to rapidly provision and reprovision, the ability to allow developers to think operationally, to craft images of software that they can then go easily from their laptop to production and back, kind of living the dream. And Docker is real. I don't know how many people are using Docker, have messed around with Docker. And so it doesn't surprise me that so few hands go up, because Docker, for kind of the database folks, for people, let me actually phrase that more generally, for people who care about data, Docker has seemed to be a bit of a slap in the face, and we'll talk about why in a second, because they focus so much on the transient nature of containers without actually focusing on some of these operational characteristics. But Docker is a very big deal, and Docker, we think, represents the future of containers, the Docker model. Docker, as I've been fond of saying, Docker is going to do to apt what apt did to tar, apt being the package manager for Ubuntu. Which is not to say that it's not going away. Well, tar didn't go away. We still use tar, CPIO in terms of apt, but we're not going to actually, these lower level primitives aren't going to go away, but Docker is going to be the way that we ship software. Containers are going to be the way that we ship software. So this is the future, we think. But if you look at Docker, and the reason why so few hands went up, I would say, is because Docker has not paid attention to things like security, persistence, performance, things that actually we care about in SmartOS. The things the reason that we've developed OS-level virtualization is because of those things, and those are the things that they've been less interested in. So what people are doing, and people are so kind of disinterested from the Docker and Linux perspective in making containers secure, that there's a horrifying trend right now where people are running containers, Docker containers, inside of hardware virtual machines. Please don't do this. God is very angry that we're doing this. It's like God's like, I gave them containers and they're doing what? God, this is why I give you disease and war, people, because you still don't learn. So we must stop angering God by running containers inside of virtual machines. Because the container revolution is allowing us to get that bare metal performance. That is the container revolution. And when we run that in a hardware virtual machine, we undermine effectively all of that. So, I mean, seeing that and knowing how angry God was, sometimes he confides in us or she confides in us, we thought, can we somehow take all of the advantages of SmartOS and mate that with the advantages of Docker? So in SmartOS, we've been container native since our inception. It's multi-tenant secure. We focused on persistence with ZFS and so on. So we've got this terrific, terrific layer. Can we somehow mate that to Docker? Can we take the best of all worlds? Can we take Docker images and deploy them on the metal in SmartOS zones? That would give us production-proven security. It would give us on-the-metal performance. So it would be a huge win. Can we do this? Can we dream the dream? Well, there's some obvious obstacles. Obstacle number one, Docker is not a Linux-specific technology per se. The reality is that it was born on Linux, and all of the Docker images that are out there are Linux binaries. So Linux, and it's fine, it's great. Linux is kind of the lingua franca for applications, right? I mean, it makes sense. And SmartOS is Unix, but it's actually not Linux. And the differences here, this is where you can come sit on my knee and I can tell you tales from the Unix wars. The differences are all kind of like total inside baseball BS that are basically decisions that were made when I was 2 years old that are now have cast these hugely long shadows. So the differences here are, on the one hand, very minor, but they're significant in that you can't just run a Linux binary on SmartOS. So the question that we had is, well, maybe we can do that. Maybe we can find a way to run Linux binaries natively on SmartOS. And we actually resurrected a technology that had been developed at Sun back in the day called LX-branded zones. And we resurrected that. And actually, in fairness, we actually didn't resurrect it. A member of the community resurrected it. One of the great advantages of being open source is that you never know when a rainbow-colored pony is going to come running through your source space and poop out a rainbow that kind of lands on your lap. You're like, wow, thanks, pony. The pony kind of flies away. And in this case, the pony pooped out a rainbow they resurrected a technology that we developed back in the day that we kind of assumed wouldn't work anymore because it was developed a long time ago. And in part because this guy in the open source community didn't actually know that it couldn't possibly work, he just got it working. And we kind of saw it like, oh my God, he's actually running Skype and so on via LX-branded zones. This technology actually could be taken to its logical completion. And that's what we did over 2014. We took this technology to its logical completion, allowing you to run Linux binaries natively. This is actually a tweet from October of last year. This is someone running XFCE. I don't know what that is. I guess that's software. Plus Firefox, plus Skype desktop on Ubuntu 14.04, running on SmartOS. So running all those binaries on SmartOS. And you get the full SmartOS toolset. You're now running on top of ZFS. You've got dtrace. You've got all the goodness of SmartOS. And he's actually running dtrace in the terminal over there, running dtrace on Skype and so on, and watching the BBC. And you see that, and you're like, okay, well, that seems pretty cool. I think people are going to be interested in this. It turns out people were really interested in this. This is just some dude. Please don't show this tweet to my kids. I can feel that my kids are trying to discover the word shitballs, but they don't have quite enough frontal lobe development to kind of conceive of it. But if this were to land in my household, it would be a match on a hot, dry prairie. So please never show this tweet to my kids. But it is amazing, and we got it working. We got to the point where it's like you can just take arbitrary Linux binaries and run them, so which is terrific. So that solves problem number one. Okay, Linux binaries, check, we can run all those. Next question, we've got to be able to deal with the provisioning problem. So the way Docker works is that there's a Docker daemon, and Docker, and it's a little bit goofy because Docker is a single program that is both a client and a server. You're like, oh, really? It's like, yeah, okay, really. But so there's a single program called Docker, and Docker actually provisions these containers for you running on the server. And the thing is that when we run a software called Smart Data Center, which runs our entire cloud, that's also open source, and that runs an entire cloud, the control plane is what provisions actual instances, provisions zones. And we're kind of not going to take software, download it off the internet, and run it in our control plane. Thank you very much. Because if you're in the control plane, you can kind of delete the company. And we would just rather the internet not have that opportunity. Thank you very much. So when we're looking at this, we're like, God, running Docker, taking this Docker binary, and actually somehow running it on compute nodes in a multi-tenant cloud really does not feel right. It's got a lot of embedded kind of Go and Linuxisms that we're really going to have to take a baseball bat to this thing to make it work. It didn't feel right. It felt like we we hoped there was a better way. And fortunately, in kind of taking Docker apart, we discovered there was a better way, because actually, on the one hand, this is one program that you run both on client and server. On the other hand, they're separated by a pretty clean remote API. And that actually gave us an opportunity. So this remote API is clean enough that we could take the server portion and throw it away and implement our own server that would actually sit on the head node of Smart Data Center, sit on the head node of this actual software that runs our cloud, and we could speak the Docker remote API. Now, what this would mean is when you go to provision a Docker container, normally you anger God and you run the Docker daemon inside of a hardware virtual machine. And so that thing just owns that whole machine. But when you take the Docker daemon, throw it out, implement the API on top of an entire data center, your containers are no longer provisioned on one VM. They're provisioned across the entire DC, the entire data center. You've effectively virtualized the notion of the Docker host. And one of the questions we had is like, are people going to find this acceptable? And as we talked to folks in the Docker community, we learned that no, not only would this be acceptable, this is highly desired because it gets you out of this hassle of having to manage virtual machines. When you go to provision, you can just manage containers, just provision containers. So this was clearly going to be a huge win. We thought this was going to be a huge win. So we implemented that for Smart Data Center, all open source, implemented all of this in the open, and we got all this working with what we call Triton. And you've seen, if you're wondering what that thing is under your butt, if you take that out, there's I think you got a little Triton placard there. This is Triton. Triton is the combination of SmartOS, Smart Data Center, the Docker Remote API, and stitching that all together in a holistic container-centric, container-native experience. And so with Triton, all you manage is containers. We stood Triton up in our US East 3B data center. We are currently in the process of rolling that out and making that generally available. And people have been very excited about it. The reception has been terrific to it because they no longer have to manage virtual machines. You are only managing containers. And again, this is available for you to try out yourself. In terms of the, and actually I'm going to come back to this slide because I want to jump ahead to containers and Couchbase. So the Couchbase is a great fit for containers. Why? Because the software itself understands elasticity. The software is great at being able to grow itself dynamically. And you care about performance. God bless you. I know I'm in my own tribe when I'm among those who actually give a damn about performance. Who actually care about computers and care about actually making them fast. The people who just actually, I would like to say just are professionals, which is great. So you care about performance, and because you care about performance, because you care about elasticity, containers are exactly the right fit for you. The problem is the Docker vessel as deployed today is the wrong fit. Because if you want to grow your Couchbase cluster, you can't just provision a new container on an existing Docker host because it will provision that container on a Docker host that's already running your stuff. You're like, no, I'm trying to grow out to a new computer. And so the existing Docker model really doesn't work for it. What you actually want is the ability to just provision a new container, and Triton allows you to do that. So Triton is a really, really, really good fit for Couchbase, we think. And when we look at what Couchbase has done upstack with the ability to accommodate elasticity, and what we've done downstack with the ability to provide that elasticity, it feels like such a good marriage that it merits a Broncos fan coming to the 49ers stadium to talk about it. So, and again, there's that little eye twitch. But we think that this represents truly containers not compromised. In terms of the future of the landscape, some of the stuff is unclear in terms of the way service discovery is going to work and so on. But what we have seen is that by providing this really solid, low-level building block, that we can actually, and especially when you made it to software like Couchbase that is so ready to become elastic, is so built around elasticity, that by providing that really low-level building block, you can build out a whole system really quickly. And this is much easier shown than actually described. So what I'm going to do, and I'm going to actually do something I've never done before. Normally, I would just always demo live, but knowing that our time is somewhat limited here, what we've done is Casey Bisson, who is over here somewhere, there's Casey. So Casey and I have been working together on this on Couchbase plus Triton over the last couple of weeks and got some great stuff. And we decided that that we would actually record Casey demoing this stuff. And this is a video this is a blog entry that Casey, you posted yesterday, right? So you can do all the things I'm going to show you, but and I'll explain what we've done in terms of we've compressed the time just a tiny, tiny bit. But so I'm going to play this video. What we're doing here, the first thing that Casey is going to do is he's going to set up Docker on his machine. And I've actually got Docker set up on my machine as well. Actually, let me just show you what that looks like. So let me pop up I got a terminal over here somewhere. So if I just run Docker, for example, I'm going to run Docker info, and what this is going to do is this is talking to our data center in US East 3B, and this is I'm seeing the actual the Docker that is running on the data center. Now, this Docker is totally elastic. Fortunately, they used to have us provide all of these things like, hey, out of curiosity, what Go version are you running over there? And of course, our daemon, it's like, what do I say? I'm not written in Go. I'm in Node. What do I say? Just say something. So we just kind of like, we're making shit up, basically. Fortunately, we don't have to do that anymore. And there are kind of fewer things, but like we're kind of making things up at what operating system, I don't know, smart data center. But what we're going to see is, and I'll play the video here. So Casey is going to first set up all of his Docker stuff. He's running SDC Docker setup here, and he's getting himself all set up. And what this is going to allow him to do is allow him to easily provision on the cloud using Docker. You can see all these environment variables that he has here. Once these environment variables are set, you're good to go. So here he is running Docker info just like I ran it over my shell over there, and now he's good to go. Okay, so what's the next thing? So the next thing is that we're actually going to go to a repository that Casey's developed that has got really simple stuff. There's not a lot of magic here. This is we call it clustered Couchbase Containers, and the key bit here that Casey has developed is a description of the Couchbase service. So you can see this docker compose.yaml file. So let's look at that YAML file. This YAML file describes a couple of services. Console is a way of registering services, and there's, of course, your actual Couchbase. You can see which ports are open and so on. And this is a Docker construct. This is a Docker compose construct that Casey has generated. And what he's going to do, and he's got this start.bash, and you can see how it's running that Docker compose command. That Docker compose command is actually going to vivify this thing. So it's going to take this description of a service, and it's going to create these actual running containers. So he's going to run that, and again, it's Docker compose that's doing the heavy lifting here, and using that description of the service. So here he's pulling the images, pulling the Couchbase image, and again, we're talking to, he's got his own image repository, and then now he's talking to the actual data center, creating containers. Now, this part of the video, we've compressed a little bit, but not much. Compressed it only to fit in a Keynote. And in fact, when we ran this just before going on, I'm like, actually, let me run this myself on my laptop and see how long it took to run. I've got it over here in a window. It only took 2.5 minutes to actually spin all of this stuff up. So all you're going to see, this entire start.bash took 2.5 minutes when running in real time, and I think it's going to be like a minute here, Casey, right? Casey kind of, so what Casey did here, this is kind of clever, is as soon as he saw that the Couchbase was up, he used the max open command to actually open the URL in the browser, and now we can see our actual Couchbase here. So this is the Couchbase that he's provisioned, and again, this is like compressed, but not compressed by more than a minute or two. This is basically real time. And so now you can see down here, he has created Couchbase 2 and Couchbase 3, and there they are. They're coming up now. And you can see that these new nodes coming up, and we've already begun to rebalance. And this is where you get to really a huge tribute to Couchbase. And I've obviously known about Couchbase for a long time, hadn't actually played around with it myself. As I was watching this over the course of the last couple of weeks with Casey, I'm like, wow, this is pretty great. I could just spin up a new node and like tell the software about it and immediately start shuffling things around. So it's pretty great. And here we can see we're actually rebalancing the 3 nodes. And so we're rebalancing our data. And I think actually Casey is going to spin up a benchmark as well. So now he's running Docker Compose PS, which is a kind of an homage to the PS command on Unix. And you can see all of the containers we've got here. And actually, I'll run that. I'm actually going to pause the video here. And I'm going to run that myself because actually, like I said, I spun this up shortly before we came up here. So if I run PS, and this is actually running, this is not canned, this is actually running an actual PS, and you can see these are the containers that I've actually spun up. So I've got the benchmark container. Here's the console container that is serving as the repository or as the service registration. So this is what these things are talking to. They talk to console to figure out where to orient themselves and figure out where they are. And then you've got these 3 Couchbase servers that have come up. And again, this just scales. I mean, this is kind of the beauty of of this is that once you, now we're back in the kind of the Casey video here, once you have all this infrastructure working, you can just scale it out. And actually, Docker Compose gives you a very easy way to just say, hey, I want to take that service that I've described in that YAML file. I've got that Couchbase service that I've described in the YAML file, and I actually just want to scale it up. So we can see, and I think there we are, we're going to scale Couchbase equals whatever. So Couchbase equals 7. So now we're going to go from 3 Couchbase containers to 7. Again, this part has been slightly compressed, but compressed by no more than a minute or two. These things spin up actually quite quickly. They identify themselves quickly, and what we'll see is we'll kind of come back here, and we will see these things begin to. Here we are. They've attached themselves to the cluster, and the cluster's already beginning to rebalance. So you can see that actually, this stuff actually works. It's actually pretty great, and you can actually go do this yourself. You can do this today if you want. You can grab Casey's repo. The blog entry describes how to do all this stuff. You can pull it all down yourself and actually do it yourself, which is actually the best demo. The best demo is actually you running it yourself. And what you'll find, I think, is what we have found, which is that Couchbase and Triton are actually really good fits for one another. And as we kind of look to the future, we think that obviously OS virtualized containers are the future of infrastructure, are the future of elastic infrastructure. They are the way to achieve bare metal performance and still getting elasticity. And as a software base, as a community that cares very deeply about elasticity and performance, we're going to be best friends because we think that the Triton infrastructure, again, all open source, is a great fit for your infrastructure, all open source. And we're really excited. We've seen a lot of energy around it, a lot of people really interested in this. So with that, thank you very much.